Okay, so we're here to talk about recovery from exercise and basically how we return back to our pre-exercise conditions. And essentially what happens during exercise, the easiest way to talk about it is to say that in order to get started, right, in order to provide our body with ATP to start movement, you essentially borrow energy from maybe other resources, um, so that you can start moving while the body is figuring out what type or how much ATP that it needs to maintain that workload. And so immediate sources of ATP are going to be from that phosphagen system. So the phosphagen system essentially helps us get going while the aerobic system determines essentially what the oxygen requirement is. And then you may also produce a little bit of lactic acid as well in the early stages of exercise. And if you ever hear anybody say, "Oh, man, the first 2 minutes of work is hard," and that is because during that first 2 minutes, essentially your body's trying to figure out what the demands are. And so you're using a lot of different energy resources to help with those demands. And then because of that, you essentially have to pay back those demands or recover from those demands in the long run. So let's focus on the high intensity exercise first. And well, let's talk about the differences in high intensity exercise versus prolonged exercise, where prolonged exercise will be glycogen restoration. So essentially what you do is this oxygen deficit and epoch during moderate and heavy exercise varies. And so on this first slide, essentially what you are looking at is that um, this is what we call steady state exercise. So the way that you want to think about this is, let's say I take you to the treadmill, I put you on the treadmill at a speed of 6, and I say you're going to run for 30 or for 6 minutes here. So essentially what I've just said is that in that first 2 minutes of exercise, your body's really trying to figure out what is happening. It's trying to meet the demands that the body is placing. And so what are those demands? The body's trying to figure it out. So you're not necessarily using oxygen, you're not using that aerobic system as your primary fuel source at this moment. You're actually using things like lactic acid and phosphagen system in that first 2 minutes. During that, you make an O2 deficit because your oxygen demand, what your body really needs, is not being met. So you essentially go into debt in the first 2 minutes of exercise. Once your body, you have like carotid arch receptors, you have different receptors throughout the body that pick up and determine how much oxygen you need. And once that takes a little bit, or once that circulates and your body figures out what the demand is, so long as you don't change your intensity, you can meet your oxygen requirement. Your aerobic oxygen or your aerobic ATP will meet the aerobic ATP demand. And so you'll maintain that, again, so long as you don't change any exercise intensity, right? If I just put you on the treadmill at 6 and I tell you you're running for 6 minutes, 20 minutes, you'll meet your oxygen demand, right? And that's still less than what your highest VO2 max is that's maintainable. If I immediately stop you, what's going to happen is you'll see this decline in oxygen uptake, right? We're saying your oxygen uptake stays slightly elevated. You'll see a quick decline in it, and then you'll see it start to taper off. So what this is, right, the elevated oxygen consumption post-exercise, this is your debt repayment here to match your deficit that you create early on. So what do you do in this rapid component? It takes a couple minutes. Look at that, about 2 minutes here for phosphagen restoration to restore your phosphagen here. And then as it starts to slow down, as it starts to taper off, the slow component is going to be removal of lactate or lactic acid. So you see some changes occur here. Where you're not necessarily back to baseline until, if you look here, maybe about 4 to 6 minutes after exercise. But because you met the requirement, you don't make too much of a debt. So your repayment here is pretty quick, right? 4 to 6 minutes. Now, when we're looking at meeting your highest attainable VO2 max, so let's say I put you on the treadmill and every minute we grade this and we make the test harder and harder and harder. Essentially, what you do here is you never allow your body to meet the demands that is necessary. And the reality of the requirement of oxygen that's needed in order to meet the highest attainable VO2, right, in order to meet ATP production is extensive beyond where you could even ever hit. And because of that, you make this really large oxygen deficit doing really high intensity, heavy exercise. Why? If I'm never meeting my VO, or if I'm moving towards my VO2 max, if you remember back to that chart that we had about the energy continuum for running a mile, essentially when you hit VO2 maxes towards 80 to 90% of your VO2 max, you're using primarily anaerobic energy in order to maintain the last couple minutes of that workload. And so you do become fairly anaerobic and utilize a lot of phosphagen system and a lot of lactic acid to maintain that 80 to 90% of your, or 80 to 90 to 100% of your VO2 max. What does that mean? That means that after moderate and heavy exercise, you have a longer epoch due to the energy systems that were used to produce that work. And so you'll see you still have a rapid component where you see a rapid decline in oxygen uptake after exercise, but you see it significantly start to slow, and it's still at, what is this, 14 minutes after exercise, you still haven't hit baseline. And that's because of all that lactic acid accumulation, all the phosphagen system that you were using. It takes a really long time to repay that. So it goes rapid for phosphagen restoration and slow for lactic acid clearance. Essentially, the more lactic acid that you accumulate, the longer your recovery is going to be because you have so much lactate to clear. Now, I think I mentioned in a previous video that this is essentially how a place like Orange Theory makes their money. And that is based off of what they say. And it's, I mean, the science behind it is smart in that they work you at high intensity and at intervals, and you burn more calories after or while you're resting because your body is working on achieving pre-resting or pre-exercise conditions. So your oxygen uptake will stay elevated throughout the day, and it takes 5 calories per 1 liter of oxygen expended in order to recover. So elevated oxygen uptake means elevated caloric expenditure. So that's the science behind their business. Here's some other factors that we could see contributing to high EPOC. And so you can take a look at that. So let's look at phosphagen restoration. This is the restoration of ATP and creatine phosphate. So funny enough, it's ATP that replenishes phosphocreatine. So if we remember this system, creatine phosphate breaks down into creatine and phosphate to make more ATP. Now, what happens during exercise, when you stop exercise, you're going to have a surplus of ATP produced aerobically. And we take that ATP that you use aerobically and that ATP that you use aerobically, we will actually use that energy to attach creatine and phosphate back together to store it as creatine phosphate. And so how long does that take? It really only takes a couple of minutes. If you look over here, here's your bucket empty, right? You have used all the phosphate, just say this is high intensity exercise. You use all your phosphocreatine, you have minimal moles left. And in about 2 minutes, you see that that will fully recover, right? So your replenishment of ATP And CP will take only about 2 minutes, 2 to 3 minutes for most of it to recover. So how does the lactic acid process occur? Essentially, when you are doing incremental high intensity exercise, you will see that you'll have incremental rises in lactate as exercise intensity increases. And then there will come a point where lactate production is exponential in comparison to the linear increase in the beginning. And that sudden rise in lactate is known as the lactate threshold. And essentially what's happening is that early on here, this linear increase, lactate production, we're able to clear as quickly as we're producing it. Over here, it becomes exponential due to more anaerobic production of ATP. And because of that, we're unable to clear lactate at the rate that we're producing it, and it exponentially rises. So this is at anywhere from 60 to 100% of your VO2 max. And this actually becomes a limiting factor because if we can't clear out lactate as fast as we're producing it, you will eventually fatigue. And so from a standpoint of training, a lot of individuals want to know where their lactate threshold is because they hope to eventually push it over. And if we could push lactate threshold over to the right, maybe able to work out at higher workloads for longer periods of time, your body adapts to buffering out the lactate and you can run at faster speeds for longer periods without that lactate accumulation. So what happens with lactate threshold? Essentially, you have low muscle oxygen. You're using a lot of it to produce ATP early on. Now we start to lose oxygen. Glycolysis starts to accelerate toward fast glycolysis. You have more fast twitch fibers to produce higher forces, and we can't clear out lactate as fast as possible. So lactic acid takes a long time to recover. We have an active and a passive version. And the most significant thing that we can do with lactate is that after we use lactate and produce it, and this is why cool down is so valuable. When you produce lactate during recovery, we can actually recycle it back to pyruvate. And if it's pyruvate, right, if you're doing a cool down, pyruvate can become an acetyl. We can go through aerobic metabolism and we'll produce carbon dioxide and water. Right, so the best way to remove lactate during recovery is to recycle it back to pyruvate and use it aerobically, right? We don't have to use any more glycogen to break it down. We've already produced it. We just need to cycle it back to pyruvate. This is typically done during low intensity exercise. Some other methods, right, some more passive methods would be to recycle pyruvate to an amino acid and it'll produce a protein. You can return it back to glycogen and store it, and then some of it will come out in your sweat and urine. So there are a bunch of different fates. What I ask you to know is not necessarily the details of this, but just to know that it can recycle to protein, glycogen, sweat, and urine. And then you want to know definitely that it will, through a aerobic recovery, can recycle back to pyruvate, and we can use it to make aerobic ATP during a low intensity recovery, which I will talk about in more detail. So this is the importance of a recovery. And when we say recovery, it's like 35% of your VO2 max. So it's not something super heavy. And lots of research has been done on this, right? So following intense exercise, the lactate clearance, this teal line right here, is significantly removed doing light exercise, 35% of your VO2 max, right? That's just like a walk. Versus no exercise, lactate accumulation stays elevated. Here's a swimming study that was done at Cal State Fullerton. And the swimming study shows 3 different types of recovery: resting, electrical stimulation, right? So you put the little e-stim pads on the body and then turn those on. So it's just moving the muscle. And then swimming recovery. And if you look at this 20-minute post-recovery, our understanding of this is that any movement was better than no movement at clearing lactate, but swimming recovery was most effective, then e-stim, and then the resting recovery was least effective at clearing lactate. And you see that here. Here's just the recovery, remaining lactic acid. So in order to clear out lactate faster, low intensity, right, doesn't have to be high, low intensity movement clears out lactate faster than no movement at all. So recovery from exercise, returning back to pre-exercise conditions, occurs because of an oxygen deficit. And after that exercise, you go into excess post-exercise oxygen consumption, or EPOC. And what happens, we have phosphagen restoration, right, which will take minutes, and then lactic acid, which will take hours. And then you see kind of what the options here that we just talked about. So a couple other things to look at on here in regard to the energy continuum and how this applies to movement. You'll see with it simplified over here, there's very specific sports that are maybe leaning more towards 100% of one type of energy source. But you'll see there's kind of, if you look at basketball, if you look at soccer, there's different percentages of the anaerobic to aerobic. And this is valuable because of the way that we approach training and the way that we approach competition. Right? So if we look at the energy system, phosphagen system, we say football, pure phosphagen, 100 meters, weightlifting, phosphagen based, right? You don't need these people to go run miles. It's not going to benefit their performance, right? We need to be really power focused. Lactic acid system, basketball, ice hockey, 400-meter run, 100-meter swim, you're going to produce a lot of lactates, things like lactate clearance, getting them used to buffering, that's going to be beneficial. Aerobic down here, right? Anything greater than that 1 mile run will be purely aerobic. And so if we look at something like running a mile, we know that most of it is aerobic, but there is still an anaerobic component. And so when we talk about this, right, you're going to have, how do you train that 40% anaerobic? And the other question is, when do you implement that 40% anaerobic? And so when we talked about that energy continuum running a mile and the differences in the respiratory exchange ratio and the energy contributions dependent on the conditions in the muscle, the same thing applies here. Essentially, when you are running a mile race and you're running for time, the idea is that you do not want to produce lactate really quickly. You want to postpone the time that lactate threshold is put into place, which we just talked about. And so you're really going to focus on aerobic system first, and then to lactic acid, and then to phosphagen system. That is ideal. If you use anaerobic, if you use lactic acid too fast, essentially you're going to have to slow down and you're going to have to clear out that lactate. So it becomes an inhibitory, it inhibits your performance the faster you produce lactate because of that lactate threshold. And so here's a good example of that. This is a 400-meter swim. And what you're looking at here, the split times, and how each split time you essentially want to get progressively faster, but you don't want to speed up too much that you produce too much lactate. And then at the end, you want to have that full burst of lactic acid, phosphagen system contributing. And so you see this here, they paced and then they blew up at the end, versus here, this individual, if you look, they went too fast here. Look what happens. You have to slow down because of that lactate that you produced. And then they couldn't ever get it back. They failed to improve at the end of the race, so they were beat. Same kind of concept here, right? This person went too fast for their physical body to clear out the lactate. And because of that, they had to slow down, versus this individual maintained, and then at the end, they were able to increase. All right, so you want to maintain aerobic for the first part, then slowly increase to lactic acid, and then at the end, you're going all out. You save it for the very end. Blow up too fast, you're going to have to physically slow down to clear out that lactate. All right, so what are our adaptations to anaerobic training? We've talked about this before. Adaptations to the phosphagen system, your capacity is how much ATP you have, and this can be increased due to ATP and creatine phosphate stores. So we're not saying significant amount, or we're not saying 100% the amount, but there is a pretty significant amount that can be improved upon, about 25 to 40% due to fuel storage increasing. And then you can also increase muscle mass in order to help this storage. Power is going to be how quickly can you make the ATP. And this is usually due to enzymes. You're only as fast as your enzymes or your teammates. So creatine kinase, our rate limiting enzyme. ATPase breaks down ATP. And then just another one on here, myosin kinase. This helps with the myosin actin crossbridge attachments. It basically means that if we're fastly producing ATP, we also need to be able to move quickly. So that helps as well. But you see basically a 20 to 35% increase in power production due to the enzymes. And we know that you can supplement with creatine in order to increase your capacity. Adaptations in the lactic acid system, capacity is increased due to how you buffer out the lactic acid, right? So how you neutralize it. But also, it sounds silly, but physical and mental tolerance for lactic acid accumulation. So it does create that burning sensation. And if you have a higher mental tolerance for it, you may be able to push through and maintain ATP production. Most people slow down and stop when they start to feel that burning. Remember, lactic acid is not bad. The more that you produce essentially means you're making a lot of ATP. We just want to be really good at clearing it so we can continue making the ATP. Power, again, enzyme-based, two enzymes, phosphofructokinase and phosphorylase. Right, and these are phosphofructokinase, rate limiting enzyme, phosphorylase starts glycolysis, and you can increase your power 30 to 60% from enzyme activation. So that's pretty significant. And bicarbonate ingestion can increase your capacity. Bicarbonates buffer out lactic acid. All right, so those are your adaptations. How do you get adaptation increases? If you look down here at the bottom, high intensity, anything greater than 85% of your VO2 max, interval sprint training, intervals of 45 to 90 seconds, recovery relief periods, 2 to 3 times longer, sometimes shorter. Basically, produce lactic acid as best as you can in order to get used to clearing it out. All right, aerobic training. Let's look at the capacity here. This is all glycogen based, so it takes hours to replenish glycogen, or sorry, days to replenish glycogen, usually based off of dietary food sources. And so we know that you can increase intramuscular storage of muscle glycogen 50 to 250%. All right, so carb loading is a thing. But the big thing is intramuscular storage of triglycerides, because the easier source of, or the more fat that we have essentially leads to this fat mobilization, which we'll talk about shortly here, which is the using fat as fuel at higher exercise intensity. So you'll be able to adapt to this process. So capacity, fuel. Power is blood and oxygen, right? More blood flow and more oxygen delivery equates to faster ATP production and the electron transport. Myoglobin facilitates oxygen diffusion. I like to think of it as muscle oxygen. And then more mitochondria, right? So your body, I always like to think of your body as like Cal State Fullerton, right? When Cal State Fullerton at 2 o'clock seems to be a busy time to get out of there. Because I feel like all the schools around there get out at that time. So 2 o'clock, every school in the neighborhood gets out and it creates a traffic jam. And what would be really nice is if we have more roads so that you don't have this traffic jam. Well, your body does adapt to this traffic jam, and it does so by improving more roads, right? You get more blood flow. And not only do you get more blood flow, but you also get more mitochondria, right? So you get more sites to uptake that oxygen. So we have increased amount and activity of mitochondria. This is where the ETS is taking place. And then because of that, your concentration of the Krebs cycle enzymes, which happens in the mitochondria, increases. More electron transport enzymes because more mitochondria. And then we have more beta oxidation enzymes as well. So that's pretty significant. If you're looking at those percentages, there's a lot. And so just to give you an idea, right, your untrained students, I'm sorry, even if you think, well, most of you are going to be in this range right here. We're talking like elite training. So most of you will be in this range. And then if you look up here, everyone's about double your oxygen uptake that is trained physically. So that's why someone like Kopchegi, who ran a 2-mile full marathon, 26 miles, took him 2 hours to do that at a speed of 12. Versus it took me 2 hours to run 13 miles, half the distance. Our VO2 maxes, his was double mine. So his power, his aerobic system was significantly better than mine. And then most of ours, actually. How do you train aerobic adaptations? Moderate intensity, right? You need to actually train at high enough intensity of continuous training to improve your power and oxygen uptake and to mobilize that. Your body has to adapt. So you don't really want to go at a really low intensity. The goal is not to just walk. Our aerobic adaptations, you typically have to push yourself at a little bit higher, 75 to 85% of your VO2 max for a long duration. So how do we mobilize fat? How do we primarily use this? Well, what happens is, like I said, you get more roads, right? You get more blood delivery and more mitochondria. And what that does is it slows down the muscle that is slows down the blood that's getting to the muscle. And because of that, our free fatty acid transporters are increased, and that allows for more free fatty acids to be taken into the skeletal muscle. And you can use more free fatty acids, and in which that's our beta oxidation, right? Free fatty acid, stearic acid. The more that we have delivered, what that does is it's going to spare your plasma glucose because we have more free fatty acid ability or usage ability. All right, you've survived bioenergetics. This is the last set of material for your exam, and your exam will be next week. You'll have the entire week to take the exam. All right, that's it.